Buoyancy is a worry when we're dealing with weighing in the lab, and so imagine a ball that is immersed in liquid and is floating, so it's not hitting the bottom. We know that the ball itself, or the object, will have a force due to gravity down. We call this force the weight. And what prevents it from hitting the bottom is the buoyancy force that is pulling in the opposite direction. And the buoyancy force basically arises from the fact that the object itself displaces a mass of water or a weight of water, and this corresponds to an upward thrust or an upward buoyancy. Excuse me, I didn't spell buoyancy correct. So what's this got to do with weighing? Well, imagine you place a mass m on a balance, and you do it in vacuum. Then the balance actually reads, in this case, m. Now, if you take the same balance and you place it in air and you read the weight of the mass, you actually get a different reading, m prime. So this is what it reads. And it turns out that m prime is equal to the mass of the object itself minus the mass of the air displaced. So the mass of all the air that would fit inside of this object we just placed on the balance pan. So the larger the object is, the larger the amount of air displaced, so the more the difference between the true mass m and the red mass m prime is going to be. Now, it turns out that we can do a calculation and we can show how the true mass is related to the mass we obtain on the balance. And the equation's kind of long, and we don't have to understand it fully, but we can understand it conceptually. The true mass of the object will be related to the observed mass via a correction factor. And the correction factor looks something like this. It's very close to 1 for a lot of objects, but for high precision work, we have to actually deal with it. It is 1 minus the density of air divided by the density of the calibration weight, I'll just call that W, divided by 1 minus the density of air divided by the density of the object itself. So just add some little notations on here. So this is the density of air, approximately 0.0012 grams per milliliter according to the CRC handbook. The density of the calibration weight. Okay, now the calibration weights are often made of brass, and brass has a density that's very close to 8 grams per milliliter. Again, the density of air we saw before, and this is the density of the object being weighed. Now we can see here, if the object being weighed has the same density as the calibration weight, then the top and the bottom will be identical, and so the observed mass we see will be equal to the true mass. So if we're always going to be weighing things like brass on our balances, we don't have to worry about this buoyancy factor at all, so everything's totally fine. If we weigh things that have a density lower than brass or greater than brass, this is going to lead to a shift in the observed mass compared to the true mass. So let's do a calculation just to get a feel for what kind of value we're looking at here. So let's imagine we're going to make a buffer. And tris is a commonly used primary standard used to measure concentrations of acids. And tris has a density of about 1.33 grams per milliliter. So we can see that is completely different than the density of brass, 8 grams per mil. And maybe we see the apparent mass, so what we actually weigh, is 100 grams. Okay, we might say, what is the true mass? So it's amazing all these things we have to worry about in analytical chemistry. So our balance says 100 grams, but we have to be aware in analytical chemistry that because of buoyancy, the mass of the objects we weigh on a balance is not the actual mass of the objects themselves. So we can calculate it using the equation given on the previous slide. So we basically take the observed mass and we multiply with this correction factor, so 1 minus the density of air. All these densities are in grams per milliliter, so I'm going to leave the units out. This is the density of brass, 8 grams per mil. Again, all the densities are in grams per mil, so we can leave them out. And divided by 1 minus the density of air, divided by the density of the tris by itself. So the tris, 1.33. So if these were the same, the apparent mass and the true mass would be identical. So let's go ahead and crunch that on our calculator. Maybe you can pause and double check and see if you get the same number. Alright, I get 100.08 grams is the true mass. So that's pretty amazing. So our balance is 100 grams, but when we apply this correction factor, it's really 100.08 grams. So you're looking at a 0.08% difference there. So if you were doing a calculation, you were changing the mass of the tris to moles, and using it to calculate the concentration of an acid or a base, you'd be off by 0.08%. So this is 1 part per 1,000. This is 8 parts per 10,000. So you'd be 8 parts per 10,000 off, or 80 parts per 100,000, or 800 parts per million off if you didn't make this correction. So this is a figure from your book. So this is the buoyancy correction. Essentially, this is the ratio of the true mass to the measured mass. So whenever this ratio is bigger than 1, it means that the true mass is actually heavier than what you're weighing. And whenever it's less than 1, it means that the true mass is actually lighter than what you're weighing. So here's the density of 8, where the calibration is made to. So we can see if your object has a density of 8, there's no error at all. And as you notice, as your density deviates from 8, you see that your measured value and your true value start to deviate more and more. As the density object becomes smaller and smaller, the error you see is higher and higher. So if you're weighing water on your balance, you're actually off by 0.1%, okay, whenever you're making a measurement. Sodium chloride, which has a much higher density, you're only off by a fraction, maybe 0.03% at this point here. And silver nitrate, quite dense, density of 4.5, you're only off by maybe 0.004%, let's say. So it's not a large effect, but it's easily correctable, so we should, if we care about the precision of our data.